Welcome to Electron Online, and here's a brand new topic for us in physics called electromagnetic induction and Faraday's law. And to introduce that concept, we're going to start with the concept of magnetic flux. Now, we've probably seen that before, but let me go through it again. Let's say that we have a magnetic field called the B field. Let's say that's directed from left to right, and that's let's say that it's uniform throughout, and there's the B field. And let's say that I have an opening, or maybe not an opening, but maybe like a conductor in a rectangular shape. So here's my conductor in a rectangular shape, in such a way that the B field can go through it. Like that. Here's my B field. And the flux going through the conductor here, the flux can be defined by this Greek letter phi, that is defined as the product of the B field times the cross-sectional area. And of course, when we multiply or have a product between vectors, we actually are dealing with a dot product here. So this means that this is equal to the strength of the B field times the cross-sectional area times the cosine of the angle between them. Now you say, okay, how can you have an angle between a magnetic field and an area? Well, every area has a directional vector which is perpendicular to the area of the plane. So if I imagine that the plane is perpendicular to the B field and there is a vector pointing out away from it, here's the vector. We can call that the unit vector, and maybe just call it, let's just have it like this. I call this A with a little hat on it. So that would be the unit vector. That's the direction of the perpendicular vector to the plane. And of course, if the B field is parallel to that direction, that directional vector, then B times A times the cosine of theta simply becomes B times A, because the cosine of theta in this case will be equal to 1. If we have a different situation, if we have a situation where we have the B field like this, and the area of the plane is tilted like this, and now what I'm doing is I'm drawing it in such a way that you're just looking at the edge of the plane, then you can see that the area is directed this way. There's my unit directional vector of the area, and this is then the direction of the B field. And you can see that there's an angle between them. Let's call the angle theta. Then in this case, you can say that the flux through the area is equal to the strength of the B field times the area. And of course, if we then multiply this out, we get B times A times the cosine of theta. And you can see that in this case, the cosine of theta is not going to be equal to 1, because as the area tilts more and more and more, you can see that less and less flux goes through it. And eventually, when the area tilts completely in this direction, so let me do that example. Here we have the magnetic field. And now the plane of the area simply is flat like this. So in this case, no magnetic flux can go through the field because the area now is perpendicular, like so. Now you can say that the flux through the area is equal to B dot dA, or B dot A in this case, which is equal to B times A times the cosine of theta. In this case, the cosine of theta will be 0, so this is simply equal to 0. No flux going through the area that way. So the amount of magnetic flux going through an area depends upon the amount of, or the strength of the magnetic field, and how the area is oriented. And of course, also depends on the size of the area. The bigger the area, the more flux you have through it. The stronger the magnetic field, the more flux that goes through it. And of course, if the area begins to get tilted, you're going to get less and less and less flux through it. And eventually, when it's tilted so that the B field is perpendicular to the directional vector of your area, you have 0 magnetic flux going through the area. All right, so now you have a concept of what magnetic flux is and how we calculate it. It's simply how much B field goes through the area. And of course, if the area is on its side and there's no way that the B field can go through it, then the sum will be 0. Okay, now let's do an example to introduce to you the concept of electromagnetic induction.